during our difficult time. Thank you for your time. Thank you that you find the time and joining to our call. And thank you, Shabs, that you find the time I know that you are very busy in this time. And thank you that you find the time to explain us few things about the ionophores, about the few topics around the antibiotics. Shabs, he graduated in the United Kingdom in 1992. He is an expert in human infection disease. He has experience in FDA in US. He 10 years ago joined to ECHO as a chief medical officer, and now he is also a LANCO expert in topic of coronavirus. So if you can Shabs few sentences at the very beginning about the situation with the coronavirus, your point of view. So microphone and it's your.
Brilliant. Thank you very much, and thank you everyone for joining the presentation. So my background is basically I've trained as an MD, as a medical doctor, specialized in antibiotic resistant infections. Practiced for 8 years. I worked in the FDA for 3 years in Washington, and then joined Elanco 15 years ago, working purely with the antibiotic portfolio in Elanco. I still practice as a medical doctor, and so I do work on and off. And yes, in the last few weeks, I've been helping out in the UK as well on the weekends on the coronavirus wards. So as most of you know, the virus, it's a new virus. We're still struggling to understand and learn more about it. As most of you know, 80% of the cases are genuinely mild cases. Of the 20% that do end up in hospital, 15% are severe cases, which means they probably need a respirator, but not a ventilator. So the difference being that with a respirator is just a mask covering the face and oxygen going in. As long as you've got a good seal around the mask, you're generally okay. And we're tending to do that if oxygen saturation is above 85%. If saturation drops below 85%, starting to go below 80, that's when we'd class it as severe respiratory syndrome, and we put the patient on a ventilator. Only about 5% of the patients do end up in a ventilator. And even of those 5%, we're seeing a death rate of about 1% overall. And that 1% is based on the positive confirmed cases at the hospital level. So don't forget, there's going to be thousands of people that are at home that have not been tested but have mild symptoms, and we suspect for every positive test there's probably 8 to 10 non-reported. So if you factor all those numbers in, then the mortality we're reckoning is going to be probably about 0.7%, which is still a high mortality given how many people are being infected at the moment. There's a desperate there's a desperate need at the moment to get a vaccine, but we're also looking at existing therapies. So I think most of you have probably heard Donald Trump made the statement that hydroxychloroquine seemed to be working, and that was a very bad statement to make because it's got everyone panicking, and people in the US have been trying to buy hydroxychloroquine. We've had 2 people die. We've had people across Asia buying hydroxychloroquine and self-administering. The problem is that usually we'd give hydroxychloroquine 400 milligrams once a week for malaria. What was used in China was on 34 patients, and they were using 200 milligrams twice a day for 10 days. And it causes blindness, it causes kidney problems, and we've seen a whole group of people across Asia being hospitalized because of chloroquine poisoning. But there are studies going on, and they want to see if this is going to work, and if it does work, then they will control the dosing and have strict monitoring on the patients. But again, it doesn't mean you should all run out and get chloroquine. The data is not actually looking that good at the moment. From 80 patients in a smaller trial done in France, only they had a recovery rate of less than a quarter. And they weren't sure if it was actually because of the chloroquine or just the patient's immune system. Another paper we've seen at the moment, the patients on chloroquine are showing 1 day less of temperature and 1 day less of severity of infection. Given the toxicity of chloroquine, that doesn't make it a very promising option. 1 day less doesn't really help too much. But anyway, so that's where we are. In terms of vaccines, there's a lot of people out there looking at vaccines, but given the challenges and the clinical studies that need to be done, we are genuinely about a year away from getting a vaccine. And then it will be given on a priority basis. So medical staff and so on before it gets moved down to the general public. So it could be another flu season before we see a vaccine, which means going into summer next year. Having said that, don't forget that the numbers that you see every day reported, especially with the number of deaths, that is a consequence of infections that happened 3-4 days before. And you shouldn't read too much into the daily numbers, because the daily numbers will fluctuate high and low. It's the overall trend that's important, and most importantly, it's how many new cases that are being observed on a daily basis. That needs to be monitored. So excuse me. So that's a bit of the background on the corona stuff. And if you do have questions, please type it in or ask. And even as we go through the presentation, if there's any questions that you have, please do just ask, stop. And I'll also stop throughout the presentation just to see if everyone's okay. So the presentation itself there's a lot of stuff going around with ionophores, and does the use of ionophores cause problems with antibiotic use in human medicine? Is there resistance to ionophores? Does that resistance go through the food chain? And so we're going to talk a little about what's true and what's not. And the subjects we're going to cover basically at a high level are what is an antibiotic versus an antimicrobial. We'll then talk about the mechanism of action and mechanism of resistance with respect to antibiotics. We'll then cover a bit of the same with the ionophores, so how ionophores work, and truly, is there resistance to ionophores? And we'll end up talking about the risk assessment process. So as we look at national guidelines on responsible use of antibiotics, they all now require that pharmaceutical companies and other authorities conduct a risk assessment to assess the true risk of using that drug with respect to compromising antibiotic use for humans. So it's a very complex process, but we'll try and simplify it and make it so it's quite easy to understand. So we'll start off with definitions of antibiotics and antimicrobials. Let's see if I can move this out of it. There we go. So when we talk about antimicrobials, in the strictest definition, an antimicrobial is a product that has activity against a microorganism, which means it's got activity against virus, fungi, parasites, and bacteria. And then embedded under the umbrella of an antimicrobial, we have antifungals, antiparasitics, and antibiotics. And antibiotics are molecules that specifically, at a therapeutic dose, have activity against bacteria. So you can have an antiparasitic that can work against a bacteria if the dose is high enough, if the concentration is high enough. However, it's then got to be tolerated in the human body as well. So it's talking at therapeutic doses. So an antibiotic is a molecule that has activity at therapeutic doses against bacteria. This slide is one that's very often used by the European Medicines Agency. And it's a very nice overview, and it just puts into context what I've just said. So you've got your antibacterials, which are then characterized as critically important, highly important, and non-important. We have the antivirals. We then have the antifungals, and then we have the antiparasitics, which are actually split into wormers and antiprotozoals. So I'll focus firstly on the left-hand side of the chart, which is purely talking about antibacteria. So this is the WHO's critically important antibiotic list. It's in its 6th revision. So this was published at the end of 2018. It actually came out around Easter time 2019. The first document came out in 2005. So about every 3 to 4 years, the WHO update this document. And what this document has done, and this is a summary, is that it splits the antibiotics into 3 groups, and then there's an annex at the end of the document. So you have what's known as critically important antibiotics. So these antibiotics are critical to human health. You have highly important antibiotics, and then you have important antibiotics. And then we have an annex which lists antibiotic classes not used in human medicine. So when we talk about terminology, all these antibiotics, except for the one in green, would be termed medically important antibiotics. So if a antibiotic class, let's just take, randomly choose one, let's say the plurimutilins. If you had one country in the world that had one registration for a plurimutilin, by definition, the whole class becomes medically important. So all these antibiotics here have a registration in human medicine somewhere in the world. We then have these antibiotics, which are called non-medically important. So nowhere in the world has any of these antibiotics got a registration to treat any human infections. And this includes topical administration as well. And these are the terminologies that both the WHO and the OIE use, and this is the definition the FAO and a lot of other organizations use. So when they talk about medically important antibiotics, they don't necessarily mean critically important. So critically important would be a subset of medically important. So when we say that you can use medically important antibiotics in the food chain, typically we would be referring to this group and not this group here. And then obviously you've got your non-medically important antibiotics, which are antibiotics not used in human medicine. And this becomes important when we start talking about risk assessment, but also when we start looking at mechanisms of resistance in bacteria. So we'll come on to that in a few minutes. So in terms of classification of ionophores by other agencies, no one across the world has, well, no one in Europe has defined ionophores as antibiotics. So if you look at the EP-RUMA definition, they have said antibiotics are compounds with a direct action on bacteria used for treatment or prevention of infections. We have a similar definition from the HMA, which is the head of medicines agencies across Europe. They have a similar definition that says ionophores would be classed as antimicrobials and not as antibiotics. This was a document that came out of the French agency, and the question was asked of them that if you raised antibiotics, if you raised meat antibiotic free, would that include ionophores or not? And this was the response that they had given, and this was given on the 22nd of September. And they said that when we talk about feed additives and so on, they talk about antibiotics, but that does not include anticoccidials, which are not strictly classed as antibiotics, but are rather classed as antimicrobials. So you've got different agencies across Europe giving the same message that ionophores are not classed as antibiotics, but they're classed as antimicrobials, which is a very different category. Are we all okay so far? If we have questions, please do stop and ask. So we'll move on to antibiotics and resistance itself. So this is just a general slide. It's not all encompassing, but these are some of the major classes of antibiotics that we have on the market today. And then within each class, you would have molecules. So if we go back to the WHO list, and you see the WHO list do not rank based on individual molecules, they take the whole class. So if we looked at let's choose the aminoglycosides randomly. From these three molecules, I mean, there's about 12 or 13 aminoglycosides, but if only one of these aminoglycosides was used in human medicine, it becomes medically important as a whole class, not just that molecule. Now, if we look at antibiotics, antibiotics are actually very, very simple molecules. They're not complex in any way at all. And all of these antibiotics basically can be put into one of four mechanisms of action. They will either inhibit protein synthesis, and these are some of the classes of antibiotics that do that. They will inhibit RNA or DNA synthesis. So you've got things like fluoroquinolones. They will inhibit biochemical pathways. So for example, the sulfur drugs or trimethoprim, or they will inhibit bacterial cell wall synthesis. So things like the beta-lactams, the glycopeptides. So on the whole, antibiotics are not actually very complex molecules. They're very, very simple molecules. And because they're simple, for every mechanism of action, there's going to be a mechanism of resistance. And for each mechanism that's been described as a mechanism of action, bacteria have developed a mechanism to combat that mechanism of action. And we only have 4 or 5 mechanisms by which bacteria confer resistance to antibiotics. They will either degrade or inactivate the antibiotic. They will pump out the antibiotic when it comes into the cell. You can have target cell mutation, so the antibiotic doesn't bind, or you've got target amplification. So they're very, very simple. Antibiotics don't have a complex mechanism of action, but the mechanism of resistance is fairly straightforward as well when we look at the antibiotics that are currently on the market. So when we talk about resistance, the first thing to note is resistance isn't created by man. Resistance has been around for a long time. It's a natural process. It's a process by which bacteria evolved to survive. It's basically Darwinian principles. So if we think back to how penicillin was discovered, Alexander Fleming was working in his lab. He'd got a petri dish. He was growing Staph aureus. He'd left the petri dish. He'd gone away for a few days, came back, and there was a contamination on his dish, and there was no bacteria growing around the mold that had contaminated the dish, and that led to the discovery of penicillin. Well, it's a natural mold that made the penicillin. All the antibiotics that we have are some form of a natural product that has been created by nature. So it's not surprising that other organisms that live in the same environment would have a mechanism of resistance to help them survive in that environment. So this is a paper that came out in 2011, which was a fantastic paper. It was a group that did some studies in Alaska, and they dug down into the soil and they carbon dated the soil to see how far back they could go. And they got bacteria going back to 30,000 years from the soil. What was more interesting was that those bacteria also carried resistance genes, and typically they found resistance to beta-lactams, so the penicillins, tetracyclines, resistance to the glycopeptides, so resistance to vancomycin and teicoplanin, which we only discovered in clinical medicine in 1986. Yet those resistance genes had been around for 30,000 years. And when they did molecular work to type those genes, the gene structure and the genes were exactly the same 30,000 years ago as we find today. So humans have not created resistance. Resistance has been around for a long time. But what we have done is by irresponsibly using antibiotics, we've actually speeded up the rate of which resistance becomes more prevalent and the rate at which resistance spreads from bacteria to bacteria. So what we have done is that we've created a way for the bacteria to spread resistance more quickly. So the resistance has already been there. It's not something we've developed, but it's just the fact that we've helped it to move along faster than it needed to happen. Is everyone okay so far? Any questions?
Yes, Shabbs, there's a question in the chat box. So it's, what about countries like Denmark? How do they look at ionophores?
Yeah, Denmark classifies ionophores as an antimicrobial as well. And that's the standard definition across all of Europe. So there's no variation between European countries. It comes under one regulatory legislation, and the terminology is the same across the board. The only region that does not class ionophores as an antimicrobial is the USA. And the reason they do that is they only have one classification. And the classification is antibiotic. They don't have the differentiation of antifungal, antiparasitic, or anything. It's just everything is, it's not even antibiotic, it's antibacterial is the word they've used. So besides the US, and again, it's just the way their legislation is, across the world, everywhere else, it's ranked as an antimicrobial. So hopefully that helps answer.
Shabbs?
Yeah.
It's Mark. Hi, Shabbs.
Hi, Mark.
If I may, it's if we talk about regulation, in the EU, you have two main regulations. You have veterinary medicinal products regulation,
yeah,
which concerns any veterinary medicinal products and antibiotics used to cure, prevent disease are under the VMP regulation.
correct.
On the other side, you have the feed additive regulation.
Yeah.
And this feed additive regulation is the one that take care of ionophores, but also enzymes and so on. In US, you don't have these two regulations. You just have animal health product regulation, I would say. Maybe Shabbs could find the word. And this includes all feed additive and VMP. So there's no, they do not distinguish between both categories. And the difference in EU is that VMP regulation, you need to have a vet prescription before to use it. And feed additive, it's part of feed. And so there is no need for vet prescription, whatever is the product. And ionophores in EU, they are feed additive and they are antiparasitics. Even if they may have some antibacterial activities like have essential oils or bleach or whatever. They are used as antiparasitics, so they are classified as feed additive. Does it give you some more clarity? Yes?
Yes.
I'm taking that as a yes, Mark. Thank you. Any other questions?
Yes, Shabbs, just a curiosity. So how they are treating in US the other antifungal or antiviral products, yeah? Because, okay, it is also, there are also the antimicrobials, yeah? So
yeah. But there's no currently, so the pressure currently lies purely on the antibiotics. All these discussions that are going on with respect to resistance does not encompass any of your antivirals or your true antiparasitics either. Because the other thing that we do run into is the effect at therapeutic dose. If you remember right in the beginning, I said it's that therapeutic dose that becomes an issue. And the bulk of your antivirals, if not all, wouldn't have any antibacterial activity at a therapeutic dose.
Yeah. Okay, clear. Thank
Yeah.
you.
No.
There's another question in the chat. Do diagnostic tools, vaccines, and biosecurity naturally replace big part of antibiotics at the market for next decade?
So I think we should always remember that antibiotics to begin with shouldn't be your first port of call anyway. It should be vaccines, biosecurity, hygiene, and everything else that goes on, because your aim is to prevent disease. So you've got to do everything that's possible to limit the chances of a disease outbreak. Only then, when all that's failed and you do have disease or there's a chance of disease likelihood, that you should move to an antibiotic. In terms of will we ever get rid of antibiotics, the answer is probably no, at least not for the foreseeable future. Because at the end of the day, you can have your probiotics and so on. They predominantly target enterics anyway. So your respiratory infections wouldn't be affected by your probiotics. And there's not many things that we have. I mean, even with vaccines aren't 100%. As long as you don't have resistance, antibiotics will give you 100% efficacy. Vaccines, we might see 70, 75% efficacy. So it's not that antibiotics will totally be replaced, but yes, there is a move, and I think it's rightly so, that we do need to reduce the amount of antibiotics that are being used. And just by basic, biosecurity, hygiene, feed management, vaccination, that does have a big impact as well. Does that help?
Yeah, I think so. So there's another one.
Mm-hmm.
How it is possible that some bacteria will be resistant for garlic, onion, and similar extracts commonly used recently?
Oh, you mean how likely is that to happen?
Tomek, can you explain what you meant?
Yes, that's my question. That's now it's a lot of different called, let's say, green products used as some bacteriostatics, like onion extracts or garlic. Yeah, that's also possible to get by bacteria some resistance for these drugs, these medicines, these substances. Yeah, or not?
So the question is, do they actually work under a disease environment, or is it purely an in vitro phenomenon to begin with?
No, such kind of the additives are given to the feed, some extras from some green products like onion, garlic, and similar ones. Yeah. They contain some antibacterial or bacteriostatic ingredients. Yeah. It's also possible that the bacteria could be resistant against it. Yeah.
Yeah, absolutely. I mean, if there's going to be anything that adds a selective pressure on the bacteria, over time there will be mutations somewhere along the line that would help a subset of the bacteria to survive in that environment. It's absolutely feasible. I mean, everything's just a matter of time.
Okay, thank you.
Yeah. Okay, everyone? Okay,
so yes, we can continue.
Okay, so we'll talk a little about resistance terminology that's been used, and a lot of people do get confused by a lot of this. So the three terms that are most often people see is cross-resistance, co-selection, and co-resistance. And this goes back to that group of antibiotics that we talked about earlier, the different classes of antibiotics. So if we look at cross-resistance to begin with, in the strictest term, cross-resistance means resistant mechanisms that confer resistance to antibiotics of the same class. So for example, if you got resistance to, so if you look at the tetracyclines, you've got tetracycline, minocycline, doxycycline, tigecycline. A cross-resistance would be if you got resistance to tetracycline, and that mechanism of resistance also gave you cross-resistance to minocycline or doxycycline. So that is what cross-resistance really means. So if we look at the aminoglycosides as an example, there's about 12 different aminoglycosides on the market, and there's over 60 different resistant mechanisms to the aminoglycosides. And no single mechanism gives you resistance to all the aminoglycosides, but some might give you resistance just to gentamicin, some give you resistance to gentamicin and kanamycin, or gentamicin neomycin, or gentamicin kanamycin and neomycin. So it just depends on which particular resistant mechanism is there, and that determines if you get cross resistance to other antibiotics of the same class. So that's what cross resistance means. If we look at the other two terms, which was co-selection and co-resistance, just to understand that, we need to understand at a very high level how you go from a gene into a protein. So you've got DNA, which has got different genes on it, and it's just not practical for all of those genes in that DNA to constantly be transcribed into RNA, translated into amino acids, which are then folded into a protein. Because if that happened, there'd just be so much protein in a cell that the cell would rupture. It doesn't matter if it's a bacterial cell or any other cell. They are just not made to handle that volume of protein. So when we look at genes, yeah, so let's say this is the gene of interest that we want to code into a protein. An enzyme would come along. When that gene is activated, an enzyme would come along and it looks for a very particular sequence. And the sequence is AUG, and this is what is known as a start codon. This is where the gene starts. So the protein will start translating this gene until it comes to a stop codon. And when it hits the stop codon, it stops translating further along. So a gene can be turned on and turned off. And on either side of the gene, you have a start and a stop sequence, which determines how much of that gene is translated into a protein. So when we look at co-selection, and this gene is multi-drug resistant Salmonella. So it's got resistance to ampicillin, chloramphenicol, streptomycin, sulfur drugs, and tetracycline. And where we have co-selection is where you have multiple resistance genes all together in one piece of DNA operating under one system. So it has one start and one stop. So let's say this Salmonella is in an animal with no antibiotic pressure, so this gene is turned off. When you administer, let's say, ampicillin to the animal, this Salmonella will turn on the ampicillin resistance gene. So the protein will come along and convert this ampicillin resistance gene into a protein which confers ampicillin resistance. But because there isn't a stop sequence here, it will also give you resistance to chloramphenicol, streptomycin, sulfur drugs, tetracycline, and then it will stop. So by virtue of using one antibiotic, you are giving resistance to all these other antibiotics as well. And this is why, although we haven't used chloramphenicol in Europe for many, many years, we still see a lot of chloramphenicol resistance in gram-negative bacteria. And it's because the chloramphenicol resistance gene has become embedded into a larger number of resistance genes. And as long as we carry on using any one of these antibiotics, we will always maintain chloramphenicol resistance. And so this is what co-selection is. If we were to look at co-resistance, it's something similar. It's multiple antibiotic resistance genes on the same piece of DNA, but each resistance gene has its own start and stop sequence. So if you only use ampicillin in this Salmonella, only ampicillin resistance is turned on, all the other resistance genes remain turned off. So if we look at these two scenarios again, if you do not use any of these antibiotics for a number of years, it's possible the bacteria will lose this whole thing, but it won't lose individual genes. It will lose the whole package. In this scenario, what you'll find is if you don't use an antibiotic, then the bacteria will lose certain resistance genes if it doesn't need them. Because keeping resistance is very costly to the bacteria, because these resistance genes reside on extra pieces of DNA, and these DNA do not have a mechanism to self-sustain. They depend on energy from the bacteria to sustain them. So if they don't confer any benefit to the bacteria, there's no reason for the bacteria to keep those resistance genes. So that's the difference between cross-resistance, co-resistance, and co-selection. When we look at resistance in the strictest sense, we actually have two types of resistance. The first is intrinsic resistance, and it's not even really true resistance. It's the makeup of the bacteria that confers that resistance. So it's a natural phenomenon. So if we look at E. coli, for example, E. coli are naturally resistant to penicillin. And it's very frustrating when we see publications where the group will have isolated 50 E. coli, let's say, from poultry, and then they'll say 100% of the E. coli were resistant to penicillin. Well, that data shouldn't even be published, because you would expect 100% E. coli to be resistant to penicillin because they're naturally resistant. So that isn't really anything to be worried about. In fact, if they said there was 80% resistance, then we'd be worried, because the other 20% is probably not even E. coli, and they've misidentified the bacteria to begin with. Intrinsic resistance isn't only genus specific, it can also be species specific in some cases. So if we look at the species Enterococcus, and we look at the drug virginiamycin is a streptogramin, then Enterococcus faecium is naturally susceptible to virginiamycin. However, Enterococcus faecalis is naturally resistant to virginiamycin. So a lot of times we need to be careful when we see very high resistant numbers, because it's not true resistance that's being described. It's more than likely natural resistance, which isn't actually true resistance at all. And that data should actually be ignored. So that's what intrinsic resistance is. When we talk about true resistance, there's a couple of ways the bacteria becomes resistant. The first is that there's natural mutations in the chromosome of the bacteria. Now, this is a very stable way to keep resistance, because once you have a mutation in the chromosome, it costs energy to create that mutation. If that mutation does not have a negative impact on the bacteria, then there's no reason to spend more energy excuse me, and reverse that mutation. So once you've got a chromosomal mutation, it's a very stable way to keep that resistance. It's also a very slow way to transfer, because that resistance will only go from one bacteria to another when the bacteria multiplies. So it goes from the parent to the offspring when the bacteria multiply. And I'll give you a true example of this, or a real-time example. In 2004, the US Food and Drug Administration banned the use of enrofloxacin, which is a fluoroquinolone, in poultry. And the reason was that there was an increasing level of resistance in Campylobacter to enrofloxacin. And the concern was that if they don't stop using enrofloxacin, you'll get increasing resistance, and it is going to become difficult to treat human Campylobacter infections with ciprofloxacin, which is the analog to enrofloxacin. So when FDA banned the use of fluoroquinolones in poultry in 2004, resistance in Campylobacter was roughly 22%. By 2016, so 12 years after the banning of enrofloxacin, resistance hasn't decreased, but it's actually increased to 36%. So it's increased by 14% in 12 years, despite no fluoroquinolone being used in poultry. And the reason, or one of the reasons for that, was because the mutation or the mechanism of resistance to fluoroquinolones is a chromosomal mutation. Once that mutation has established, it will not reverse back. Now, there's a number of other things that have happened in the US, and what the current thinking is that the fluoroquinolone resistant bacteria have also acquired virulence genes, and it's made them more virulent, so they've outcompeted non-resistant bacteria as well. But the point is that once you've got that resistance established and it's chromosomal, it will not reverse back. The other way that bacteria do get resistance is by the acquisition of external pieces of DNA. And they come in the form of plasmids, which are found in gram-positive and gram-negative bacteria. They're found in the form of transposons, which are found only in gram-positives, or in the form of integrons, which are found only in the form of gram-negatives. And integrons and transposons can either move on their own, or they will jump onto a plasmid and move with a plasmid. Now, this is an expensive way of keeping resistance, but it's a fast way of spreading resistance, because the resistance not only goes from parent to offspring when the bacteria multiply, but if you have two bacteria next to each other, that resistance mechanism can multiply and then one copy go into the cell that's in the nearby environment. So this is three examples by which you get gene transfer when you have mobile DNA. So this bacteria in the middle, let's say it's a susceptible bacteria, and there's one of three ways it could become resistant. It could become resistant by transformation. And transformation is, if you have this bacteria here in the top left, it's got resistance genes, it dies, so that resistance is released into the environment, and that resistance is absorbed into the susceptible bacteria. This very, very rarely will happen in nature. We can do this in vitro in the lab, but even for this to happen in vitro, we have to pulse this bacteria with a very high voltage for a couple of milliseconds, and that opens up pores in the bacteria for the DNA to go into. So it may happen in nature, but it's very, very rare. Another way bacteria could become resistant is by transduction. So this is where you have bacteriophages. They could go into a resistant bacteria, pick up the resistance gene, come out, attach itself to a susceptible bacteria and inject the resistance gene, and the bacteria becomes resistant. This is one of the reasons there's a lot of opposition to phage therapy, because there's always been a concern that these bacteriophages may mutate and become gene donors. And we do have one incidence in the cheese industry where a Enterococcus bacteriophage has mutated. This was several years ago, and it became a donor of resistance genes. So there's a chance in nature that it could happen where if we're using bacteriophages for therapy, they could become carriers of resistance genes. The most common way for gene exchange to happen in nature is by conjugation. This is where two bacteria come together. So you have the bacteria with the resistance gene multiplies, one copy stays in the original cell, and one is transferred into a neighboring cell, making it resistant. Does that help? Everyone okay so far?
Yeah, very good.
Yeah. Okay.
There is one question, if
yeah,
we can. Does antibiotic dose affect the speed of microbial resistance?
The antibiotic dose.
Yes.
To a degree, yes. So if you've got a subtherapeutic dose, what you would do is that you would wipe out the bacteria with lower susceptibility, and that would leave the bacteria with high, decreased susceptibility. So not necessarily resistant bacteria, but this is what we would call first step mutants. So these are bacteria with a higher MIC, which isn't quite at the resistant level. And then by stepwise increasing the dose, what you're effectively doing is adding more and more selective pressure for the bacteria to become resistant.
Yeah, again, kind of curiosity, Shabbs. What for phages using this, let's say, DNA from bacteria? They are really needed, or it is just by the incidence that they are catching the DNA and they are then injecting it to another bacteria?
It's probably that bacteriophages are there to, because I mean, you know, DNA is going to carry all sorts of stuff, tolerance to UV light, heavy metals, detergents, disinfectants. So these phages could be picking up all sorts of different genes. And it just so happens that you've got a large piece of DNA that may also carry resistance genes as well.
Yeah, clear. Okay, thank you.
So, you know, it could be a multitude of things that causes these phages to be carrying all these different genes. Yeah. Okay. So there's a couple of terminologies that have been used predominantly on the human side, and they're slowly working their way into the veterinary side. And this is a paper that was published by a group of people from the WHO in 2011. And the couple of terms that they've introduced, which I've actually expanded out, and there's a few more terms now which I need to add to the list. The first one we all think of is multi-drug resistant. But multi-drug resistance is a very, very specific term within the medical and now within the veterinary community. And what multi-drug resistant really means is resistance to 3 or more antibiotic classes. So if you have resistance to tetracycline, minocycline, doxycycline, that's resistance to 3 drugs, but it's one class. So it's not multi-drug resistant. But if you had resistance to tetracyclines, aminoglycosides, and penicillins, so that's 3 classes of antibiotics. So that's what multi-drug resistance is. Resistance to 3 or more classes of antibiotics. We then have extensively drug resistance, XDR. XDR means where you've got a bacteria that's naturally susceptible, so not intrinsically resistant, but naturally susceptible to a multitude of antibiotic classes, but they now become resistant to everything except 1 or 2 classes of antibiotics. That's called extensive drug resistance. So an example of this would be something like the resistance gene NDM, which is New Delhi metallobeta-lactamase. It's a gene that was first discovered from patients coming back to the UK from India. And it's a gene cluster that gives you resistance to 11 different antibiotic classes. You only have susceptibility to 2 antibiotic classes only, but you've got resistance to every other antibiotic class that bacteria will naturally be susceptible to. So that's XDR. And the last term is PDR, which is pan-drug resistant. And pan-drug resistant is where you have total resistance to every single antibiotic class that bacteria would naturally be susceptible to. And the only case of PDR that we've ever encountered in the human setting is when we see multi-drug resistant tuberculosis. That is the only time we have seen PDR in the clinical setting. We do see a lot of MDR and we see a lot of XDR. But the only time we've seen PDR is when we see multi-drug resistant TB. So those are the three terminologies that are used more and more extensively. Everyone okay? We'll move on to ionophores, and I'll go through this bit very quickly because it's just the chemistry of the ionophores. So ionophores are a group of natural fermentation products. They've been named ionophores primarily because of the ions they bind to, and then they can be split into carboxylic and polyether ionophores. And then within that, you've got the monovalent and divalent. So this is just some basic chemistry around how ionophores are. The interesting thing about ionophores is, if you remember, we talked about antibiotics and they had 4 unique mechanisms of action. Ionophore mechanism of action does not fall into any category that your traditional antibiotics do. The mechanism of action of ionophores is extremely, extremely unique. And we can skip the large amount of texture, but basically what they do is they insert themselves. So here I've got monensin, that's what the M stands for. It inserts itself in the bacterial cell wall, and you start getting shifting of ions. So potassium going out, hydrogen going in, hydrogen going out, sodium going in, and this causes an ionic imbalance between the outside of the bacterial cell and the inside of the bacterial cell. And the bacteria then rapidly tries to rebalance the ion difference between the inside and the outside of the cell. In doing that, it needs energy. So it uses all the ATP that it has in trying to rebalance the extracellular and intercellular ion concentration. And by doing that, it basically exhausts itself of energy. So the normal biochemical processes needed to keep the cell alive don't function anymore, and the cell effectively just collapses on itself. And that's how ionophores typically work. So they are very different in their mechanism of action to any traditional antibiotic, and that's another reason that they're not classed as antibiotics. In terms of their spectrum of activity,
can I have a question?
Yeah, sure.
Just wanted to ask, the same mechanism of action is for bacteria and coccidia?
Yes, I believe that the mechanism is the same.
Okay, thank you.
There's another question.
Sure.
How to explain the situation, real example from human medicine, that pan-drug resistant Klebsiella New Delhi was susceptible to colistin.
Klebsiella. New Delhi, NDM1 in Klebsiella.
This is what's the question.
Okay, no, so when we saw NDM1 was actually resistant to colistin as well. The only 2 drugs NDM1 is actually susceptible to is a 3rd generation tetracycline called tigecycline, and it's actually susceptible to the aminoglycoside apromycin. It's not susceptible to any of the other aminoglycosides. If you give colistin in combination with tigecycline, we've seen some efficacy. We think there's some synergistic effect, but if you give colistin on its own to NDM1 infections, we've not seen clinical outcomes that are favorable. Where we've seen good outcomes with colistin is where we see Klebsiella with carbapenem resistance. So if you've got full carbapenem resistance due to CTX genes, that's where we see where that colistin seems to be working well. So in terms of NDM1, colistin has very limited activity unless you're giving it as a combination.
Okay, thank you very much.
Okay, no problem. So we don't deny the fact that yes, there is some antimicrobial activity of the ionophores. However, on the whole, ionophores have a very narrow spectrum of activity, and they only have activity against your gram-positive bacteria. So here, if you see, you've got your gram-positive, you've got activity, but against gram-negative, there's no activity, and gram-negative are intrinsically resistant to ionophores. So that brings us to the whole debate of antibiotic resistance and human food safety. And when we look at this whole debate about using antibiotics in veterinary medicine and causing resistance, the debate is not about getting resistance development which compromises antibiotic use in animals. And I'm sorry, but no one cares if you've got chicken with a Pasteurella infection and you're using antibiotics and those antibiotics don't work and the chicken dies. No one's going to care about that. Yeah, well, the farmer will, but no one's going to cry over a chicken. The concern is that, are you going to use antibiotics in the animal that's going to cause resistance development, and those resistant bacteria are going to go through the food chain and cause a human infection, or transfer resistance genes to human bacteria that can then cause an infection, which then needs treatment, and it won't respond to treatment because of co-selection, cross-resistance, or co-resistance because of antibiotic use at the farm level. So the only bacteria that we're really concerned with at this point are your foodborne pathogens. So your two key foodborne pathogens, which is Campylobacter and Salmonella, or your commensal organisms, which are E. coli and Enterococcus. And your E. coli represent your gram-negative bacteria, and your Enterococcus represent your gram-positive. And these two have been chosen very carefully because they're found everywhere and they're very easy to work with. And most importantly, E. coli and Enterococcus are actually very, very promiscuous. So any resistance gene that's likely to be found in a gram-negative, it's going to transfer to E. coli. And any resistance gene likely to be found in a gram-positive is likely to be found in Enterococcus. So the four bacteria we're concerned with in this whole AMR debate with respect to use in animals is Campi Salmonella, E. coli, and Enterococcus. Now, if we go back to the previous slide, we said that your gram-negatives are intrinsically resistant to ionophores, which means you can knock out Campylobacter, E. coli, and Salmonella from the discussion. So with respect to the use of ionophores, the concern then becomes around Enterococcus. And so that's what we will focus on. So the first thing is, we've talked about this whole intrinsic resistance thing. So the use of ionophores does not impact Salmonella and Campylobacter. So your foodborne pathogens are out of discussion. It doesn't affect your E. coli, your commensal, that's gone. It's only Enterococcus. We've been using ionophores for over 30 years now in veterinary medicine, in some cases longer, and we have not seen a single case of an Enterococcus that is resistant to ionophores. We have seen cases where they've got elevated MICs, so the MICs are higher than baseline, but they're not so high that they're reaching resistant levels. And there's a number of reasons that we suspect this is the case, especially with respect to monensin, that you probably need a lot of genetic changes and so on in the DNA of the bacteria to cause that resistance to occur. So that leads us to risk assessment and what is the true risk of using ionophores to human health. And this is where everything ties in. So all the stuff about resistance we talked about, the co-selection, cross-resistance, co-resistance, this all comes into your risk assessment. So when we're looking at risk analysis, there's three components to risk analysis. The first is obviously your risk assessment. Risk assessment drives your risk management and risk communication. And the cornerstone of your risk assessment is antibiotic susceptibility data. It's your baseline MIC data that drives your risk assessment. And a bad risk assessment can lead to bad risk management policies. So once you do a risk assessment and you perceive there to be a risk, you propose risk management guidelines and intervention policies. The only way to know if your intervention policies are working is to go back and repeat your risk assessment after a period of time. And if your resistance is coming down, then you have the right policy. If your resistance continues to increase or is stable, then maybe your policy needs to be tweaked a little. So there's three components to a risk assessment. There's the release part, the exposure, and the consequence part. And we'll go through each one specifically with respect to ionophores. So the first step is the release part. And the release part says, are you using an antibiotic at the farm level that causes resistance in one or all four of your bacteria of concern? So by using the drug, do you cause resistance in Salmonella, Campylobacter, Enterococcus, and E. coli? If the answer is yes, then you move to the exposure part. So the exposure part, so your release part is done at the farm level. Your exposure part is either slaughterhouse samples or your human-animal interface, which is your retail meat samples. And at that level, you again look for your bacteria of concern, so Salmonella, Campi, E. coli, Enterococcus, and see if you're finding resistance to the drug of interest in the bacteria of concern. So in this case, the bacteria of concern is Enterococcus. The drug of interest is ionophores. So we've got a lot of European data, and Europe's actually stopped mainly looking at ionophore resistance now in national programs. They're just not finding it, and they're saying it's too much money to invest on a year-by-year basis. So this is data from some of the major national surveillance programs. So you've got Denmark from Denmark, Moran from the Netherlands, Normvet from Norway, and this is percentage resistance. They don't necessarily look for specific ionophores. They've all mainly used salinomycin as your indicator ionophore. There's one case of monensin use and one case of narasin use. But if you look down the board, there's 0% resistance over the years to the ionophores. And this is coming out of cattle and then beef, and then Enterococcus, Faecium, and Faecalis. So this is your exposure part, and you have 0 resistance going down the board. This is coming out of broilers and poultry meat. And again, if you look all the way down, you've even got Sweden in here as well, and all the way down, 0 resistance to the ionophores. And it's again Faecium and Faecalis from the different sources. So human-animal interface, there's no resistance to ionophores going through the food chain. The last part is, and then this is just the Faecalis from the end of that. Again, you've got 0 resistance. So the last part is the consequence part. And the consequence part would be, if you did see resistance at the exposure part, is that resistance in bacteria going through the food chain? Are those bacteria causing human infections? Are those human infections needing treatment? And is the physician using the same class of drug that was used at the farm level, so you got cross resistance? Or are they using a drug for which resistance is being co-selected, or you have co-resistance with the genes causing resistance to the drug used at the farm level? So ultimately, are you seeing treatment failure because of co-selection, co-resistance, or cross-resistance? And again, if we look at the ionophores, there's very limited human data, but what data there is, there's just 0 resistance to ionophores in Enterococcus from human infections. So if we look at ionophores now as a whole from a risk assessment, we've got no release because there's no resistance to ionophores. So we wouldn't see any Enterococcus at farm level which are resistant to ionophores. The exposure part, where either slaughterhouse samples or retail meat samples, we don't see any enterococcus at that level which are resistant to ionophores. And from human samples, human enterococcal infections, we have never found an enterococcus from humans that are resistant to ionophores. So I'll conclude here and then we can go back to the Q&A. But as we said, besides the US, ionophores are globally classified as antimicrobials. They have a very unique mechanism of action. The WHO, the OIE, FAO, and all major agencies around the world class them as non-medically important. That means there is no human ionophore registration. We've had ionophores in the market for over 30, 40 years now, and we have yet to find a single report of a resistant enterococcus which is clinically resistant to ionophores. We do see reports occasionally of enterococcus with higher MICs than baseline, and there's some reasons why that is there, but we don't see enough resistance that is above a clinical breakpoint for ionophores. And we have a number of competent agencies around the world, across Europe, the US, and a lot across Latin America and Asia, that have conducted risk assessments on the ionophores. And they've all concluded that the use of ionophores in no way compromises the use of antibiotics in human medicine, either by cross-resistance, because no ionophores are used in humans, so there's no cross-resistance, but there's no resistance gene, so there's no concern for co-selection and co-resistance with medically important antibiotics and ionophores. So hopefully that leaves a bit of time for questions and discussion.
Hello, I've got a question. Can you hear me?
Yeah, Daria.
So my question is, what is your opinion? Because not all the European countries have already some legislation, some restriction about using antibiotics. And what is your opinion, which group of antibiotics will be restricted in veterinary use in the first place because of this human health?
So, I mean, one thing you've got to bear in mind is that the WHO's critically important antibiotic list is not a static list. The list is revised every couple of years. So something might be critically important in human medicine today, might not be in 5 years' time. Now, the WHO has also said that your national list overrides the WHO list. That's clearly written in the WHO document. And in Europe, we have our own critically important antibiotic list, which is the AMEG list, which was recently finalized, and we have a second revision of that list. Now, if you look at that list, the antibiotics have been ranked as category A, B, C, and D. So category D would be you can use with, responsible use of antibiotics would be drugs that are in category D. Then we have category C, where the drugs need to be used with caution. Then you've got category B, where the drugs should not be used unless there's very exceptional circumstances. And then you've got category A, where the drug should not be used in veterinary medicine at all. So we do have a guideline in place in Europe, and that would dictate what drugs could and cannot be used in veterinary medicine, and the order in which they can be used. So ideally, you would want to use non-medically important antibiotics. If this is going down the therapeutic road, if there's no non-medically important antibiotic for that particular indication, then you would try and get a drug out of group D or group C. And in very exceptional circumstances, would you take a drug out of group B? And there's got to be all sorts of restrictions and reasons why you're going after a drug in group B. Does that answer?
Yeah, thank you.
Hello, chaps. This is Holger.
Hiya.
I have a question concerning the drug resistances going from the farm level use to the human medicine. Have you got a percentage? You've shown us that for the ionophores, but for the other antibiotic classes, is there any percentage that you probably can tell us? Because we are dealing with that discussion every time we do presentations.
Yeah, so see, this is really interesting that you bring that up. So there is data available from the EFSA reports, and they publish that on a yearly basis. It doesn't necessarily indicate that resistance is going from animals to humans. So if you've got Salmonella and Campylobacter, we don't know, there is no argument that, yeah, those bugs go through the food chain, cause human infections. Yes, some Salmonella may be coming from the environment, but on the whole, we can say they're coming through the food chain. And then you can attribute resistant levels as a result of antibiotics being used at the farm level. So that data is available through EFSA surveillance programs. Which again, you can either look up on the EFSA site, or we can provide those for specific drugs if you need them. It becomes more challenging when you're looking at E. coli and Enterococcus, because those infections in humans are not all, in fact, it's very unlikely they're coming out of animals anyway. Those infections typically end up being nosocomial infections, which means patients usually catch them within the hospital setting. And that is reflected in their resistance prevalences, because they typically tend to be more skewed towards, the resistance is more skewed towards those drug classes being used at the hospital level than being used either in the community level or within veterinary medicine. The other thing that you also need to be careful with is that the bulk of the data that is being presented is actually not using clinical breakpoints. They're using a parameter called epidemiological cutoff values. So that gives you a higher prevalence of less susceptible bacteria. But agencies, including EFSA, tend to use the measuring unit epidemiological cutoff value, but they report the data as percentage resistant. So they're actually reporting a higher number than is truly clinically resistant, if that made sense.
Yes, it does. And I to be honest, I just wanted to make sure that I have the right number or right figure in my head. When I've read a paper and it said it is kind of 1.4 up to 1.5%. That will come up from the resistances coming up from the food chain to the human medicine, is it?
So I would say, if you want, I wouldn't really focus on E. coli and Enterococcus at all. I would really keep the discussion on Campylobacter and Salmonella when you get into those discussions. And I would take the data from the EFSA reports as being your probably more robust set of data. We also have the CSER, European CSER surveillance program, which is an industry-sponsored program. Elanco's part of it, and those papers we publish that data very regularly. So I'd be happy to provide you with some of those papers as well. And the reason I say stick with the CSER data or the EFSA data is that we see a lot of publications out there that will say, oh, we have 200 Campylobacter, and they're resistant to 40% resistant to fluoroquinolone. But when you then look at the details of the paper, they might have only gone to 4 farms and collected 50 isolates per farm. And so from a study perspective, that's not 200 samples. That's only 4 samples. Because one farm, one herd, one flock is 1 sample. So if you went onto a farm and collected 50 samples, that's actually still classed as 1 sample. And that's one of the problems we see with a lot of these publications as well, that either their study cohort isn't large enough, or they've collected all the samples from one farm, or only 2 or 3 farms. So ideally, if you're going to start using numbers, I would say use the industry Caesar surveillance program data and the EFSA data that's published every year.
Thank you.
Shabbs, it's Jacek speaking. One question, maybe a little bit more general. What is your opinion? How high is the risk that the other countries' authorities will share American approach to the ionophores, which we all know that it's one of the two most important molecules, yeah, in Elanco, which is monensin and narasin, and which is targeting the 2 species, yeah, poultry and cattle. So what is your, let's say, risk assessment for that that topic?
I think that the risk assessment, we've clearly shown there's no risk to human health. If anything that's going to drive this, it's going to be consumer pressure.
Yeah.
And that's what's driven it in the US as well, is exactly. The consumer pressure that no antibiotics ever, and then they drag ionophores into the discussion as well. Mm-hmm. So it's not going to be a scientific argument that's going to drive this, but I think in Europe, and if Mark's on the phone, Mark can jump in, but I think in Europe, there's less tendency now to go down that road of no antibiotics ever than there was probably 3-4 years ago.
Yeah. So.
Yes. So as you invite me, I jump in. Tendency is here. So the main issue between US and Europe is that in US, if someone wants to claim no antibiotic or res without antibiotic, he has to get rid of ionophores due to legislation, due to regulation. In Europe, and Chaps share at the beginning the document from EU Commission, ionophores are not antibiotics. So if someone wants to claim that animals are raised without antibiotic, it should say raised without antibiotic treatment, meaning that it can use feed additives, ionophores. So as said, Chaps, the danger may come from food chain. We try to manage it with market access team. The good thing to know is that is a big player like Yum, KFC, or McDonald's. Even in US, they didn't go antibiotic free, and they do consider that there is no issue by using ionophores. So it gives a tone for a global perspective because they are global groups and they have a global footprint. And so they do recognize that there is no issue with ionophores. So that's a very important point. Second point, from EU perspective, end of August last year, EU Commission published an opinion on the surveillance of drug usage in EU due to the new VMP regulation. And we didn't ask them to do that, really, believe me, but they said that for monensin, it was not useful to follow the cells of monensin because there is a keystone in EU, and they said that monensin should not be in the surveillance of antimicrobial usage in Europe compared to all other antimicrobials, because it's so safe that there is no reason to do it. So really, I think we are on the safe side.
Yeah, okay. Thank you very much, Mark, about this answer. Yeah, it is really, really important, and especially I see that it's quite, let's say, safe for Europe or European Union. Yeah, my question is coming from, let's say, from Russia. Yeah, because Russia is maybe it's not very strict about the antibiotic usage at the moment, but we also hear the rumors which are coming to us that Russia is, or Russian authorities starting to be a bit more and more concerned about the general antibiotic use. So I'm just asking, what is the risk that they will also take into the consideration the ionophores? Yeah, let's say like a follow-up on the American approach. Yeah, so this is something what I afraid.
My gut feeling is I don't think it's going to happen.
Mm-hmm.
Yeah, I think we've done. I know across Asia, market access has done a good job. Across Europe, our market access guys have done a fantastic job to secure ionophores. I just don't see the threat to ionophores short term, even probably long term, to be honest with you, across Europe, Russia, or the Asia region.
Yeah. Okay. Thank you, guys. Mm-hmm.
Because I think, don't forget, the other thing is that even if you look at the chicken prices and how much chicken's really being sold in the US, that's raised without antibiotics, it's a very small proportion, and there's been a lot of noise from the poultry industry to try and swing the pendulum the other way. So you've got a group of people now that have initiated the raise with responsible use of antibiotics, which keeps chicken reasonably priced, and so the consumer has confidence and they can use antibiotics. And that seems to be working well for the moment.
Okay.
Okay, there's another question. Can you confirm in US there is no official FDA CVM regulation on ionophore use in poultry? The NAE choice is food chain driven, not regulatory, is my understanding.
Yes, that's correct. There's no government mandate for it. It is purely food chain driven. It's how the food chain are defining it. It's nothing that's regulatory.
Thank you.
Hello, I'm Yanis from Greece. Thank you very much for the presentation. It was very interesting. People that know me know that I have a lot of questions, but I will have to just limit myself to two. I hope you can do two questions.
Should be okay.
Yeah, the first one is you are talking about pathogens, especially food pathogens, and I'm always thinking, are we monitoring? Do we know what's going on with non-pathogenic bacteria or even beneficial bacteria like Lactobacillus? Do they transfer this?
In terms of resistance transfer? Yeah.
Yeah.
All bacteria will do gene transfer, but it's not. It depends on the environment it's in. It depends on a lot of the circumstances that they're there. If you look at the plasmids or the resistance genes, for example, that are in your probiotic strains, they are very controlled how they're made. So for gene transfer to happen in a plasmid, it has to be initiated by the plasmid itself. So when we have these probiotic strains, the machinery that would initiate gene transfer has been taken out of the plasmids. So if you're specifically looking at probiotic, prebiotic strains, they do carry resistance genes because they need to be there for that bacteria to survive in the event of an administration of an antibiotic. But those will be attenuated resistance genes. So although they will be expressed in the bacteria, they don't have the machinery that would allow them to transfer between different bacterial cells.
Yeah, I was thinking about natural occurring Lactobacillus, but yeah, that would be a causal problem also.
Yeah, natural bacteria, yes, that's going to happen. There's nothing, we can't do anything about that from the natural population.
Okay. The second one is a more intriguing one. You had a quote that anything that is putting pressure on the bacteria would cause some defense from them.
Yeah.
And I'm thinking that the most effective pressure we can put on the bacteria is the immune system. Do we expect that they're going to find a way through that?
That's an interesting one. Well, to date, we've not seen any bacteria. I mean, they can overwhelm the immune system, but we haven't seen bacteria that have become resistant to the immune system. So if you've got a new infection and there's no antibiotic administration, then it's a challenge between how quick the immune system can respond and how quick the bacteria can multiply and damage tissue to such a degree that there's no recovery. Do you see what I mean? So if you've got an immune response, typically you'll get cytokines and inflammation. Now, if the bacteria is so much, then you start getting so much cytokine and inflammation that the body goes into organ failure.
I think it's more of a philosophical discussion now. But for example, some viruses like HIV on the beginning were mimicking the immune system, so you can say they were kind of
Yeah, that's a tough one. Not really sure what the answer to that is.
Okay, no, we don't have the time. Maybe when we meet sometime after the quarantines. Okay, thank you. Thank you.
Any other questions to Shabbs?
I have a question. It's Monica from Poland speaking. Do you think it is common situation that poultry farmers and their family and family members and staff from the poultry farms were less responsive to amoxicillin treatment when they had bacterial infections?
No, not necessarily. I mean, partly it'll depend on the bacteria that's causing their infection, what kind of infection it is. But I've seen a lot of people from the veterinary profession, and we haven't ever seen decrease amoxicillin susceptibility in those population as opposed to non-veterinary related professions. In fact, if we look at ampicillin, specifically with enterococcal infections, if it's a respiratory infection with an enterococcus, they're typically more susceptible to ampicillin if they come from the veterinary profession than if they don't.
Okay, thank you very much.
Anyone else?
Yes, I have a question.
Sure.
Yusuf from Jordan. Some countries in the Middle East use avilamycin in the feed. Let's say controlled doses daily. Can that contribute to any resistance, let's say, in the future?
Okay, so in terms of avilamycin, yes, we do occasionally see resistance to enterococcus in avilamycin, but it's purely chromosomal mediated. It is not plasmid mediated. So if that resistance goes through the food chain and that those enterococcus were to cause a human infection, it would be the same situation as, for example, well, not because ionophores wouldn't give you that, but you would not treat that human with an orthosomycin, so with another avilamycin analog, because they're not registered for human use. And because it's a chromosomal mutation, there's no concern for co-selection and co-resistance because they're not mobile pieces of DNA. So yeah, we do occasionally see resistance in enterococcus. It's not that often, but we do. But that would not compromise human antibiotic use if you go down the risk assessment pathway, because the mechanism of resistance is chromosomal.
Okay, thank you.
Looks like that's it.
Awesome.
Thanks a lot. It's been really, really good. Thank you. Thanks everyone for participating actively. It was really nice to see.
Thank you.
With that, we can continue.
Thank you, Mr. Sharp.
Thank you.
Okay,
thank you.
And thank you, Mark, for helping out.
Thank you, Shabbs. Thank you, everyone.
Cheers, everyone.
Shabbos.
Bye-bye.
Bye.
Thank you very much. Bye-bye.